The way that an electric motor works is that I've got two magnets in proximity to one another. And we know from playing around with magnets that if you do that, if you have magnets close together, they try to move. They either try to move away or they try to move to the other magnets that are close to them. Remember that a fundamental principle of electromagnetic fields is that in this case, if I have a conductor and I run current through it, that creates those lines of magnetic field around it. So if we run current through the conductor and essentially we create in the center of a motor, we have a bunch of wires, a bunch of conductors that we're running current through. So there's this huge electromagnet that we form inside of the motor. And on the outside, we have the poles, the field poles. They're either going to be fixed magnets that are situated on the inside around the edges, or they're going to be electromagnets that we can control the strength of. But in any case, as you can see here, as you can imagine, if I have these huge magnets on the outside and I put a magnet that's in the middle and it's able to rotate around the center, then it's likely to do so. The magnets north and south want to pull together, but they can't because they're fixed, because they're mounted to the inside of the motor. Kind of showing another diagram of the same thing. You see the north and south being attracted in this armature winding, and you see the north and the north being repelled. So in a motor, one side of it's being pushed and the other side's being pulled, but it's in the same directions, so you get that torque developed. And here's kind of a close-up. Here are the actual windings. All these wires right here are the windings that we're running current through. And because of that, the electromagnetic fields will develop around that. And it makes these bars very magnetic. These steel bars are laminated steel. These are the inside magnets that are trying to get away from the pole magnets that are on the outside. But now, how do we get current into these windings? We can't just run wires out from them to the real world, because if this thing starts to rotate, then the wires are just going to tangle up, get tight, and break. So the way that we get current into these windings are through these brushes, because each winding has one end attached to one of these commutator segments. These are copper bars. One of them's attached to one end of a winding, and at the other end of the winding, it's attached to another commutator segment. So we'll take the current from the outside world, we'll say from a battery, a power source, and we'll run it into these carbon brushes. Carbon brushes are conductive, and this carbon brush rests on this. As you can see right here, that brush is resting right on these commutator segments. And so the current can enter the brush into the commutator, around the winding, and come out the winding on the other side, and then back out to my power supply. And as this rotates, now the brushes come into another commutator segment and another set of windings. So as this rotates, I've got my external power supply continuously applied to my windings in the rotor, creating electromagnetic fields. Showing it in motion, the brushes riding on the commutator, the field poles, one would be here, one would be here. They're shown here on the side. So these windings that are getting current from this external supply going into these windings, and this is all becoming an electromagnet. And here are the lines of flux from these pole magnets, either permanent magnets or electromagnets. That's where these forces are created that magnets have and causes the rotation to occur. This shows a better example of poles, and these are variable fields. These field poles are not permanent magnets, they're electromagnets. The advantage to that is we can control the magnetic strength, and in doing so, we control characteristics of the motor like torque and speed. Many poles in this one. This simple diagram just has a north and south. In reality, this one has four, it looks like, two up here and there'd be two on the other side. And this one has several. This, much like this. And I wanted to go over this speed control because We use motors, we use electric motors in a lot of applications. We use them to move things, conveyor belts, cranes. We also use them to compressors, pumps. You know, the locomotives, train locomotives, those are electric. You know, they're not diesel driven. Those are electric motor driven. And yeah, they have diesel engines in them, but those diesel engines are the prime movers, which run a generator that produces electricity, and that electricity powers the electric motors in a train. And we vary the field on the generator to vary its output to the motors, and that's how we control the speed of the motor in a train. The same thing's true with barges. The tugs on the barges, we have diesel engines in them, but they're just running generators. So here's an example where we're controlling speed of a motor. Because having control of a motor speed, the torque characteristics, power, that's critical in a lot of these applications. If I'm pumping and I want to vary the flow, I've got to vary the motor speed. And if I'm running a crane, I want the hoist to slow down. Yeah, in most any application where we use electric motor, we like to be able to have control over the speed. So in this particular case, as you saw in the recorded lecture, this is a blower that's in your car heater. And the way that this is going to work is that my power is coming in through a fuse block, and eventually will end up the motor. If this is in the off position, the current would want to flow down here, but there's nothing connected at this point, so this is a dead end. But if I put it on low speed, the current could come in and travel down this path, travel on down this way into this resistor block. And it goes into the resistor block. Now here's a T. It has the option of going this way or does it? Because we get up to here, this is a dead end. These dotted lines are not electrical connections. So it gets up to here, there's no place to go. So this is a dead end. So all the current has to go the rest of the way. It gets to here, it can't go this way for the same reason. It's a dead end. So the current goes through the switch, enters the fuse block, goes through the total resistance and into the motor. The total resistance limits the amount of current that's going to the motor, so the motor speed is determined by the current. And if I go to medium speed, my path to the motor bypasses half of this resistance, because it can't go back this way. Now this is a dead end. So I go through half the resistance, effectively doubling my current to my load, to the motor, effectively doubling the work that can be done by the motor. So the speed, we'll say, is going to double, although it may not be exactly that. But you can see that by cutting the resistance in half, I'm going to double the current, and that will affect the speed of this motor. And then finally, if I'm in high, I'm going to come down here and bypass all of those resistors, and this will get full current and maximum speed. This is showing different ways you can hook up the motor field. Now remember, this field that's represented in this schematic. In this case, it's an electromagnetic field. Those are those big field poles that are on the outside edge of the motor, and that this schematic represents not the whole motor. These actually represent the brushes, these little black things on the commutator. This is the armature. So the motor that's represented here is both parts, this electromagnet that we form in the rotor or the armature, and this electromagnet that we create with the field. In this case, this is a shunt configured motor, and shunt means parallel. So the same power that we use to deliver to the field, also we deliver to the motor. Here is also a shunt configuration, but in this case, I have a variable resistor here to control my field current. Here I have a shunt motor, but I have the resistor in series with the armature, so I control the speed of the motor with the armature. If you get into motor control, counter EMF is a significant thing to contend with. And as I said in the video, Anytime you try to use a motor, it's acting like a generator to some extent, and it opposes what you're trying to do in making it act like a motor. And anytime you're using a generator, it tries to act like a motor, and it opposes everything you're trying to do to make it act like a generator. So in the case of a generator, I'm trying to turn it in a direction, but it's wanting to act like a motor as well as a generator. And as it acts like a motor, it's acting opposite direction than I'm trying to turn it. So it's pushing back on me. The more load that you put on a generator, the harder it is to turn it. And in a motor, I'm trying to put current into that motor. It's acting like a generator, trying to push that current back. Something that's a little bit counterintuitive is that I can speed this motor up by decreasing the strength of the field. And I suppose what's counterintuitive is if you think, well, you have to have field and you have to have armature to make this thing run, why is taking some of this away, making this go faster? And the reason is that counter EMF, this acting like a generator, I can reduce the generated voltage by reducing this field. And that means that it's not pushing back as much current as it was if it was generating a lot of voltage, which means I can get more current into it, which means I can make this magnet stronger, and that effect will outweigh the interaction that we lost with this. So the generated or the counter EMF will cause this to increase in speed. Just taking a look at the schematic so that you're familiar, if you see a motor starter circuit, how it works. The power supply is up here at the top. This is the field. F1 and F2, these leads would come out to the outside of the motor so that you could hook them up to a power supply, just like this is hooked up to a power supply. These are the electromagnets that are the field poles on the outside of the motor, north and south. They're represented by the single field schematic symbol. This is the armature circuit. Again, these little black things represent the brushes, and A1 and A2 are also leads, and they would come out to the real world, out of the motor, so that you could hook them up. In this case, I'm hooking it up to this control circuit, and CR1 plays a role in that. So both of these things together are inside the motor. These two things right here are inside the motor, and these leads, F1, F2, A1, and A2, come out of the motor. So in this case, I have my 110 volts. I come down here, current's wanting to flow. It's flowing through the field, so the field's energized all the time. It's wanting to flow this way, but it can't because this is open, and this is open too, but this is the only one it takes to keep this out. Come down here, wants to flow this way. It goes through this switch because it's normally closed. It gets to this point. It can't go this way because that's open, and it can't go this way because this is open. But if I push this button, that causes this coil to be energized, and that electromagnetic field closes this set of contacts that's part of this relay. This and this is all in the same housing. It's all in the same relay. So once these close, now I can let off the switch because the current is flowing this way and it's keeping itself energized. And the only way to turn that energization off, to de-energize this, is to push the stop button. That will stop the flow of the current. The magnetic field will collapse and the spring will pull these contacts apart. But not only did this magnetic coil close these set of contacts, but it also set these two contacts closed. All three of these, and maybe more, were all in the same relay assembly. So I energize this, pick it up, these close, and now current goes through here. With this magnetic field that's being created from current flowing through it in forces with this electromagnetic field in the field, the motor turns. And the only way to get it to stop is to push the button, de-energize this coil, these all drop out. This is a reversing motor. If I change the direction of the current going through the armature, that changes the polarity of the magnetic field that we create with the armature. If we change the magnetic field, then the forces of that electromagnet in here have the opposite interaction with the forces from the field poles, so it turns the opposite direction. And we accomplish the reversal of current with this configuration. As before, none of these contacts are closed, so nothing's going. The field is hot. In other words, it's energized all the time. It's a good idea to leave the field energized for a couple of reasons. For one thing, it generates a little bit of heat and it keeps the motor inside dry because this is inside the motor. Another thing, if we completely lose a field, particularly in a series wound motor, if we completely lose the field, the counter EMF will go to 0. And so there's no opposition to current flow at all. And the current will go so high in that series wound motor that the motor will accelerate and nothing will limit its speed. It'll just accelerate till it flies apart. So I want to go forward. Current comes down here. I hit F. And because R is closed, because R is not picked up, then CRF will pick up and current will go this way through F and from A1 to A2 and out. Going from A1 to A2 creates a magnetic field of one polarity, so this runs one direction. But if I close R contacts by hitting the R button, then the current flows from A2 to A1. The magnetic field is different, so that the rotation direction is different. And just a little bit about these. These are interlocks. We talked about those, I think, before, but these are safeguards. I don't want CRF and CRR to pick up at the same time. It won't really do anything to the motor, but what will happen is if F closes and R closes, that creates a dead short cross positive and negative. So I don't want that. So this is set up in a way that if R's picked up already, this opens up. And once R picks up and this opens up, there's no way F can close at the same time. And the same thing here. If F is picked up, this opens up, so there's no way that R can pick up. These are safety electrical interlocks. Some contactors have mechanical interlocks as well. In other words, you can't push this button down if this one's already pushed down. Or there's contacts in addition to these that are in the switches that will also make and break a lot like these do. This is a three-phase motor. In a lot of industrial commercial settings, we use three-phase motor. In our homes, single phase. And I've got 3 leads coming into that. And this is what the starter looks like. It's essentially a really big relay with heavy duty contacts. You can kind of see the contacts here. So my 3 leads, 3-phase power coming in, they call those phases phase A, B, and C. It's coming in here. So I've got a 3-phase, like 480 volt power circuit that comes in. It goes through these contacts here. If the coil that's in here somewhere, if it's energized, then these will close. These right here will close. And that'll allow the power that's coming in here to be transmitted down to here, where they'll go out to the motor. These are leads T1, T2, and T3. T1, T2, T3. These overloads are in here. They're bimetal strips. If so much current is flowing through any of these legs, if excess of current flows, these will heat up and it'll trip open the contacts. These 2 wires right here, you see this red wire here and this wire here, that is this coil. This is the electromagnetic coil that if we put current into this, the magnetic current closes these contacts right here, pulls these together to allow the power to go from here to here. Now note that my coil can run off of 120 volts. So I hook 120 volts to this, and I hook a 480 volts up here, because this is my power circuit, and this is my control circuit. So like the other examples we had, I hit start. As long as the overloads aren't heated up and keeping this from picking up, it will pick up. It'll close this to seal itself in, and it'll also pick up this one, and this one, and then I have complete circuit. This is a reversing starter. I've got an extra set of contacts. Still have power coming in, and I'm going to bring the power in, and I'm going to kind of run some over to these other contacts. So here's F1, F2, F3 right here. Here's R1, R2, R3 for reverse over here. But they all come down to the same output, my T leads right here going to the motor. So in a three-phase motor, the way you reverse the direction of its rotation is to change any two of the leads. You take out any two, reverse them, it'll run the opposite direction. And this is what this starter does. It brings into L1, but it runs one of them to T1 on the first round. But if I want to go to reverse, it runs it to T3. So L3 is this two. So L1 and L3 are the one we're switching. L2 just goes straight through in both cases. And the starter circuit looks similar to the other, except that I have this other coil to pick up. Two coils here. And here are those leads, these red wires. Again, this is a single phase, like 120 volt here. This is three phase, high 460, 480 volts. For the test, I'm going to need you to describe to me the best you can, the best of your understanding, how those electromagnetic fields play a role in motor and generator operation. So you may need to go back and review the little bit about generators too. Transformers, we see different kinds. Here's a substation seen outside town. And here's a coil that would go to a distributor and an older type, pole transformers, various types of transformers. They come in a lot of different size and shape and a lot of different applications. We talked about transformers before, but we're going to take another look at them here. And we know that I've got a primary coil and I've got a secondary coil. And I also know that there's a ratio of windings, how many turns in this winding compared to how many are over here. It's what we call the transformation ratio. Number of turns in the primary compared to the number of turns in the secondary. And we also know that that same ratio is going to apply to the voltages. However, the windings are directly correlated to the voltage. Whichever side has the most windings is also the side that's going to have the higher voltage. So if the primary has more windings than the secondary, it's a step down transformer. The current is the opposite way. So this transformation ratio is inverted, and here's why. Power is the same on the primary and the secondary. It doesn't matter if it's step up or step down transformer, the power is the same on both sides. And what we're actually transforming is that ratio of current to voltage, because power is voltage times current. If I have 500 watts over here and 100 volts, that means there's 5 amps here. 5 amps times 100 volts, 500 watts. And if this is a step-down transformer, and this steps it down from 100 volts to 50, which is a factor of 10, my current is going to have to go up, opposite direction of the voltage. It's going to have to go up by a factor of 10. So when I multiply the voltage times the current, I'm still going to get 500. So that's on there for you guys to think through, but that's how that works. So here's an example. I've got 150 volt on my primary, and I've got 2.2 kilo ohm load, and I want to know what's I1, what's the current in the primary. So my load, whatever I want to run, I can't do anything about the impedance or the resistance. It's 2.2K, and it runs off certain voltage, and I've picked this transformer to do that. But I need to know how much current is going to be flowing in that primary so I can put the proper protection on it, fuse or a circuit breaker. How do I find that out? This will step us through. We know we've got a transformation ratio of 2.5. That means that E1 compared to E2 is equal to 2.5. Since we know that E1 is 150 volts, we solve for E2. So essentially we're going to divide 150 by 2.5 to get E2. And we get 60 volts on the secondary. Now I can calculate the current in my secondary through Ohm's law, because I is equal to V divided by R, and I will get 27.3 milliamps by doing that. And I can then use the out transformation ratio, which is 2.5, is equal to I2 over I1. And then I know what I2 is. I can solve for I1, 10.9. So if I multiply 150 by 10.9, I'm going to get the same thing as if I multiplied 60 volts by 27.3. And because of that, I could have solved this another way. Once I figured out the current on my secondary, I could have figured out the power by multiplying 60 by 27.3. That would have given me the power that's on the secondary. And since I know that the power on the primary is the same, I could have taken that power, divided it by the voltage, 150, and that would have given me the current. Here I have a step up transformer. I know that because I've got a number less than 1. So if V1 over V2 comes up the ratio of less than 1, I know that this one's bigger than this one. But I'm going to solve it the same way. 0.5 is E1 over E2. I know that this is 150. You're going to solve for E2. I divide 150 by 0.5, which is the transformation ratio, and I get 300 volts on the secondary. Again, I can calculate the current by taking 300 divided by 2.2 to get 136.4 milliamps. I can calculate the power and then divide this voltage into it, or I can use the transformation ratio to solve for I1. Power, you see, is the same on the primary and on the secondary. All right, so something else you're going to need to be able to do is, if you're given a display like this, tell me what are the values. In this case, I'm looking for the period and the frequency of the waveform and the voltage in terms of V peak and VRMS. Let's do the voltage first. All right, the voltage, we're talking about V peak. We're talking about the distance from the 0 to the highest point. In this case, I've got 1, 2, 3 divisions. 3 divisions is not my final answer for amplitude or V peak. How much is each division worth? Well, I've got to look at my scaling to determine that. In this case, my volts per division is 0.5. So each one of these is a half of a volt. That means I've got 1.5 volts as my peak voltage, shown right here. All right, so VRMS is simply V peak times 0.707. So here I have it right here. All right, now we'll do the frequency and the period. Period's easy to do first. I'm going to count one cycle, which means from here to here. If there were a bunch of these visible on the screen, that doesn't matter. You still count just one cycle, no matter how many's in the display. You don't start at one end of the display and count to the other end of the display. You count at one end of a cycle and stop at the other end. So I'm going to count 1, 2, 3, 4, 8 divisions. In time, it takes 8 divisions for one cycle to happen. How long is one division? Well, I've got to look at my scaling too, and it's 10 milliseconds. So if I have 8 divisions and they're each worth 10 milliseconds, that's 80 milliseconds. 80 over 1,000 seconds, 81 thousandths of a second. So to get the frequency is the reciprocal. So if you use your reciprocation key, then you would type in 80 milliseconds, but you have to make sure it's 80 milliseconds, not 80 seconds. So if you're questionable how to write that out, and here it is, you can just take 80 milliseconds and express it as 80 over 1,000, because 80 milliseconds means 80 1,000ths. And then when you reciprocate it, you have 1,000 divided by 80, and you get 12 and a half. So the answer is 12 and a half hertz. So be able to do one of those. And given a circuit like this, you will need to be able to tell me voltages as it's drawn. What are voltages at different things? So if I say, what's the voltage across this? So I got 120 volt supply. If I say, what's the voltage across this on-off switch, what would you say?